What specific problem does the meta-rewarding method aim to solve in the context of instruction tuning for large language models? And how does this relate to the superalignment challenge?
The meta-rewarding method aims to solve the problem of enhancing the judging capabilities of large language models, LLMs, during instruction tuning, which is crucial for improving their ability to follow instructions effectively. This method introduces a third role, the Meta-Judge, which evaluates the judgments made by the judge, thereby creating preference pairs of judgments that can be used for training. This is particularly relevant to the superalignment challenge, as it seeks to develop mechanisms that allow potentially superintelligent ICE to be controlled and aligned with human expectations without relying heavily on human-generated data. By improving both the actor and judge roles through iterative self-play, the meta-rewarding method addresses the limitations of previous approaches that primarily focused on enhancing the actor's performance while neglecting the judge's capabilities, which could lead to issues like reward hacking. Ultimately, this self-improving framework reduces dependence on human feedback, aligning with the goals of superalignment by fostering autonomous improvement in LLMs.
How does the proposed meta-rewarding method work? Please illustrate the entire process step by step, including the roles of the actor, judge, and meta-judge.
The proposed meta-rewarding method operates through an iterative self-play process involving three distinct roles performed by the same model: the actor, the judge, and the meta-judge. First, the actor generates multiple response variations for a given prompt. Next, the judge evaluates these responses using an LLM-as-a-Judge prompt, assigning scores based on a fixed rubric and producing judgments. Following this, the meta-judge compares the judgments made by the judge, utilizing a pairwise evaluation mechanism to determine which judgment is superior, thus generating preference pairs of judgments. This process allows the model to create training data for both the actor and the judge, enhancing their respective abilities. Finally, preference optimization is applied to the collected data using direct policy optimization, DPO, iteratively refining the model's performance in both acting and judging roles.
Can you provide a simple example demonstrating how the meta-rewarding method improves upon the self-rewarding mechanisms introduced in prior research? Walk through the roles of each component with a hypothetical prompt and response.
In the meta-rewarding method, the model operates in three roles: actor, judge, and meta-judge, enhancing the self-rewarding mechanism by explicitly improving the judging capabilities. For example, consider a hypothetical prompt: what are the benefits of exercise? The actor generates two responses. Response A: exercise improves physical health and mental well-being. And response B: exercise helps maintain a healthy weight and boosts mood. The judge evaluates these responses, assigning scores based on a rubric. However, instead of just focusing on the actor's performance, the meta-judge then compares the judge's evaluations of these responses, determining which judgment is more accurate. This iterative feedback loop allows the model to refine both its response generation and its evaluation skills, leading to better overall performance in instruction following compared to previous self-rewarding methods that only focused on the actor's output without enhancing the judge's capabilities.
What are the theoretical and practical benefits of using the meta-rewarding method compared to existing methods like RLHF or standard self-rewarding techniques?
Theoretical benefits of the meta-rewarding method include the explicit improvement of both the judging and acting capabilities of the model, which is achieved through the introduction of a meta-judge that evaluates the judge's judgments. This contrasts with existing methods like RLHF, which primarily rely on human feedback and can be limited by the quality and availability of such data. Practically, the meta-rewarding method allows for a self-improving training process that does not require additional human data, as all roles, actor, judge, and meta-judge, are performed by the same model. This leads to a more robust training cycle, as evidenced by the substantial increase in the length-controlled win rate from 22.9% to 39.4% on the AlpacaVal benchmark, outperforming both GPT-4 and standard self-rewarding techniques. Additionally, the method effectively addresses issues like length bias in responses, ensuring that the model generates concise and high-quality outputs, which is a significant improvement over traditional self-rewarding approaches.
How was the meta-rewarding method validated or tested across iterations? Describe the experimental design, datasets, and metrics used to demonstrate its effectiveness.
The meta-rewarding method was validated through a structured experimental design involving multiple iterations, starting with an instruction-tuned Llama 3 to 8B instruct model. In each iteration, the model generated responses to prompts, evaluated them as a judge, and compared its judgments as a meta-judge, creating preference pairs for both actor and judge roles. The training utilized 20,000 prompts generated by Llama 2 to 70B chat, with each iteration producing 35,000 responses and 11 judgments per response. Effectiveness was measured using various metrics, including the length-controlled win rate on benchmarks like AlpacaVal 2 and ArenaHard, where the win rate improved significantly from 22.9% to 39.4%. Additionally, the correlation of the judges' scores with human preferences was assessed, showing notable improvements in agreement metrics, thus demonstrating the method's efficacy in enhancing both the actor's instruction-following ability and the judge's evaluation accuracy.
What limitations or drawbacks did the authors identify regarding the meta-rewarding method, particularly concerning the evaluation process and the potential for score saturation?
The authors identified several limitations regarding the meta-rewarding method, particularly in the evaluation process. One significant issue is the 5-point judging system, which often leads to ties due to minimal quality differences between responses, complicating the differentiation of scores. Additionally, as training progressed, responses tended to approach the maximum score, resulting in score saturation that hindered the model's ability to detect further improvements. The authors also noted that despite efforts to mitigate positional bias in the meta-judge, this issue persisted, particularly affecting the judge's performance in iteration 3. Furthermore, the judge exhibited a tendency to assign higher scores, which accelerated score saturation and reduced its discriminative ability between responses, particularly for non-self-generated ones.